Hello and welcome to another episode of TWiML Talk, the podcast where I interview interesting people doing interesting things in machine learning and artificial intelligence. I'm your host, Sam Charrington. This week's shows are drawn from some of the great conversations I had at the recent NVIDIA GPU Technology Conference, and they're brought to you by Dell. If you caught my tweets from GTC, you may already know that one of the announcements this year was a new reference architecture for data science workstations powered by high-end GPUs and accelerated software such as NVIDIA's RAPIDS. Dell was among the key partners showcased during the launch and offers a line of workstations designed for modern machine learning and AI workloads. To learn more about Dell Precision workstations and some of the ways they're being used by customers in industries like media and entertainment, engineering and manufacturing, healthcare and life sciences, oil and gas, and financial services, visit dellemc.com/precision. All right, everyone, I am on the line with Paul Mahler. Paul is a senior data scientist and technical product manager for machine learning at NVIDIA. Paul, welcome to This Week in Machine Learning and AI.
Thanks for having me.
Absolutely. I'm looking forward to jumping into our conversation, which will be focused on what NVIDIA is doing around RAPIDS and cuML and all of the interesting stuff in that area. But before we do that, you were a philosophy major. How did you make your way to working in machine learning?
I was a philosophy major, and 2 years before I was set to graduate, I added economics as a major because I read The Economist magazine and thought that it was a fascinating collection of a bunch of different articles about different aspects of the world. So I figured if that's what economists read, I wanted to be an economist. I went on to do a master's degree in economics where I mostly focused on quantitative methods. And in an earlier life, I went out to Washington, D.C., where I worked as an economist. I began my career at the World Bank, serving on health and human welfare issues in sub-Saharan Africa. And then I worked for the Office of the Chief Economist at Fannie Mae. Now, one day while waiting for the bus to get home from Fannie Mae, there was an article from the New York Times about a gentleman from SUNY Buffalo that had written an algorithm that was offering notes on screenplays. And I always had like a hobby interest in, the different creative arts aspects of our culture. And when I saw that somebody had written, essentially a big block of math and code that was telling writers how to write their screenplays better, I immediately decided that I needed to switch into data science or big data, which was the more popular term at the time, because that was where some of the most interesting things in the world were going on.
That's a great story. You remember the moment, literally the bus ride that triggered that set you off down this path.
Yeah, it was raining at the time.
Awesome. And so what do you do now?
What I've been doing for the last year, I had been at a couple of startups, and I joined NVIDIA to work on what we've been calling the RAPIDS project, or the RAPIDS ecosystem. Now, what that began as is that our director of engineering, who I'd worked with previously at Accenture, for years had been saying that, we see this great acceleration in, neural network methods as a result of getting them on GPUs. But you are not seeing any of those advantages for more of like the bread and butter data science that happens at a lot of places, like Fannie Mae or like the World Bank, where they may have large data sets and questions they want to address through machine learning, but we aren't talking about convolutional neural networks to understand images. So, a lot of the time when I was working at a data scientist at a couple of startups, I like to joke that I was really a bar trivia champion, because while I was waiting for my code to finish running and spit out my result, I had plenty of time to read all the news of the world on the internet. Um, and I guess, unfortunately for me and my compatriots in data science, what we've done with cuML and cuDF in particular is, if somebody knows pandas or they know the PyData ecosystem, they can immediately jump right in and start seeing just crazy speed ups, like 50x, like sometimes more than that, on doing their end-to-end workflows, and that includes reading from disk to GPU memory, doing all your data munging and merging and variable creation, through actually executing your algorithm and making inferences. So the idea was that since all of this, well, I mean, some of it is not obviously tractable to GPUs. We are able to process strings in the latest iteration of cuDF, which to me seems like a miracle. But I like to joke that it's kind of like before, the team that I work with had delivered these big pieces of cuDF. It's like I could drive a car, and now suddenly I can fly a plane, and I don't need to be an expert in CUDA or parallel algorithms or anything except the tools that I've worked with most of my career.
Now, let's take a step back. Maybe when I introduced you, I mentioned cuML, you've mentioned cuDF, mentioned RAPIDS. Can you kind of paint a picture of the broader ecosystem of software and libraries and tools that comprise or make up RAPIDS, and how they all fit together?
Yeah. So RAPIDS is the overall name of the project, and that's made up of smaller sub-libraries that all start with cu because that's inherited from CUDA. RAPIDS is built on NVIDIA CUDA.
And CUDA is for anyone who's not familiar, it's the
yeah.
underlying library or API for doing things on NVIDIA GPUs.
Right. It's the general purpose computing library for NVIDIA GPUs.
Okay.
And if you think about the more broad PyData ecosystem, I think a lot of people do a lot of their initial data cleaning and exploration in pandas. And so that's what cuDF is meant to replace for people that are moving their workloads onto GPUs. And so the API is very, very close, and you're able to, in some cases, just change the import statements at the top of your program, and it will just work.
And so Pandas has this kind of core abstraction of a data frame, and so cuDF is just a kind of, you can think of it as a CUDA-powered data frame?
Yeah, I think that's the best way to think about it.
Okay.
cuML is our machine learning toolkit, and we aspire to one day have almost all the functionality that exists in Scikit-learn. Scikit-learn is an eminent package built by some of the world's greatest developers, so we've got a ways to go there. But we've been rapidly adding algorithms in the last release. For example, we have stochastic gradient descent regression, ordinary linear regression, ridge regression, principal components analysis, and some other things like Kalman filtering. What we're trying to do is start with the things that are the real workhorses of day-to-day machine learning in business and other parts of industry. And it's been exciting to watch the package grow. In fact, when we launched back in October, we had, I think, 4 algorithms in cuML, and we've doubled that over the last couple of months. It was very exciting to present at the GPU Developers Conference in San Jose, California, a couple of weeks ago to the wider community, all the things that we had been able to deliver in such a short amount of time.
You mentioned that you kind of aspire to Scikit-learn. Does that mean that cuML replaces Scikit-learn? It sounds like it does for folks that are trying to take advantage of the GPU. And was there an opportunity to, rather than replacing Scikit-learn, kind of fit in underneath it so folks that use that API or that have existing work that uses Scikit-learn could take advantage of the GPU acceleration without having to rewrite their apps?
I mean, at least with the algorithms we've delivered, we've tried to keep the API one-to-one.
Okay.
For any of your listeners, I would encourage them to take a look at the API and just see how close it is to Scikit-learn. I'd also like to add that we've partnered with NVIDIA, the French research institution that does a lot of work on Scikit-learn. And over the next few months and few years, we're going to be building that collaboration with them. I don't think we'll ever replace Scikit-learn because there are still problems where I don't think it's big enough or the use case is right to necessarily go to full GPUs. So I think of certain analyses I did as an economist, which would look like machine learning, but were maybe a few thousand rows. And this was much more traditional frequentist statistics. I think that there's always going to be a lot of that work being done. And I think that, with any data science work, it's about finding the right tool for the job. But I will tell you, when I was testing out our code earlier in the summer, our demo workflow involved reading in, I think around like a gigabyte of CSV data to pandas. And on my MacBook Pro, it took like 5.5 minutes. And on a single GPU, it took like 15 or 20 seconds.
Wow.
When you talk about, data analysis is a iterative, interactive process. And the faster you can move, the more fluid your conversation with the data will feel to you as a user. There won't be, the long wait times to see your results or see if you made a coding error in my case or any
less
of the
of
other
an
things.
opportunity to become a bar trivia master.
Yeah, it's shucks.
So before we dig into that, because that's an interesting point there, we were kind of talking about the landscape. You mentioned cuDF, cuML. Are there other major pieces that we should be keeping track of in this conversation?
Yeah. We are working on a graph analytics package called cuGraph. And
I could have guessed that.
Yeah. Our minds are so fixated on accelerating the algorithms, we're totally out of bandwidth for fancier names. But
everyone knows that Jensen does all the naming at NVIDIA, so why would anyone else spend any time thinking about that?
But cuGraph is embarrassing in the sense that we compare it to a graph analytics package in Python. And it's one of those things where you see the numbers, you just really want to double check them, like 10,000 times speed ups over network X for certain algorithms.
That was my reaction to the loading the data frame. And I want to get through the kind of broad landscape before we dig deep into that. But that's the first place I'm going to come back to once we do. So you've got a graph analytics piece in cuGraph. Any other major components here?
Some of the things that began as major components are now under the hood. So we put a bunch of effort into building a string reader. So you could directly parse data sets with strings. It's a very common thing that happens in data science. GPUs do not like strings. But now you can do things like just easily create your dummy variables from strings on the GPU, which sounds kind of ho-hum, but it's actually a pretty major achievement. And it's just part of the whole speeding things up. I don't think our case would be as compelling if we said that it could only be numerical data in the cuDF data frame. That simply will not work for many use cases. So we also have a package called cuCrossFilter. It's written as cuXFilter, and we're going to be building out some GPU accelerated visualizations. So if you think of the workflow from munging to analysis to insight through visualizations, we want to be able to offer every piece of that puzzle. The other thing, we're heavily using a software called Dask, and Dask is a package that handles distributed computing. It has been used to scale out pandas, for example, to multiple cores. And we were lucky enough that the creator of Dask has joined our team and is helping us use that as a way to distribute workloads when we're talking about moving beyond a single node of GPUs.
Let's maybe go back to that initial example you gave of loading the pandas data frame or loading the data frame. You said it was a terabyte?
It was a gigabyte.
A gig.
It's pretty easy to choke pandas, and I'm sure a lot of your listeners have experienced this before. The workflow was Fannie Mae makes loan delinquency data going back, I think, 16 years available for free, and this is the whole payment history for a subset of all the loans that Fannie Mae has acquired. And as a demo workflow, what we wanted to do is read in, however many quarters of data we could fit or were relevant, and then apply XGBoost to predict default. Which reminds me of another sort of under the hood improvement that we've made. It's not really under the hood, but we have made contributions to the DMLC XGBoost library, and we'll continue to do so. That has appeared in a lot of our early presentations and webinars. I think XGBoost is almost like magic, and it's a good broad workhorse for the first thing that we were going to introduce. But we are working with the community to make certain changes to XGBoost that make it more amenable for the RAPIDS ecosystem, but then giving those back to the community. So pardon that sidebar, but with the before any real data processing had happened, just bringing in this dense, large data set, as a rule of thumb, we couldn't do more than a couple of quarters of data. And then you would really see the time to like load and go through the data preparation and execute the algorithm increase substantially. So I think that the largest we could do on pandas quarter-wise was like 2 or 3 quarters of data if they were small. So I think the biggest we tried was about 1.5 gigabytes. And that's where you saw those, really kind of frustrating load times of more than 5 minutes.
And so what's happening here in these two different scenarios is on the Panda side, you've got a gig and a half, or on both sides, you've got a gig and a half of information on a disk, probably a CSV file, perhaps.
Right, that's correct.
And you're loading it into a data frame. On the Panda side, it's a data frame that's located in RAM. And on the Rapid side, it's a cuDF frame that's located on the GPU itself. Is that right?
Yep, in GPU memory.
Okay. And that's where the kind of the 5 minutes versus 15 seconds differentiation comes from?
Yeah, and this is where this really is more for like our hardcore C guys, but there's some problems with pandas that have been known for a while. It's great. Like I can't thank Wes McKinney and the community enough for open sourcing it, because it's, put food on my plate for 5 or 6 years, but it's also single threaded on the CPU. So even in the world of CPUs, you started to see people look for things like Dask to help, better leverage even the multiple cores of CPUs you might have on your MacBook Pro. I think it's kind of funny. Every data science gig I've had, they've given me like a shiny MacBook Pro, and I mostly work in Jupyter notebooks, and most of that stuff is only taking advantage of a single core of the processor.
Right.
I mean, I don't want to exaggerate too much, but it's almost like
you still want the next MacBook Pro.
Well, we'll wait and see. I want to see what they do with that touch bar. I got some thoughts on the touch bar, but
let's not even go there.
Yeah. But and so the other thing is that when we move past the the massive parallelism that you can get from using GPUs, when you get to the side I know better, this is all for the most part matrix algebra, and GPUs love matrix algebra.
Mm-hmm.
They are designed to do it, and in our algorithms like doing ridge regression, which can take some time to run on in the conventional PyData ecosystem. When I gave a tutorial at the GPU developers GPU technology convention, I was just like, we're going to just do a hyperparameter search and run through like 1,000 ridge regressions on this Black Friday data set, because it's just fast enough that we can kind of brute force hyperparameter search on certain data set sizes.
And do you have comparative results for that particular scenario?
We aren't baking off every algorithm these days. Ridge regression is fast. I don't know, like doing a ridge regression on, I think, like 800,000 rows took me like, less than a second, couple of seconds. Mm-hmm. I remember it being fast enough where I could do a live demo and run through 100 iterations of it. And normally doing 2 or 3 would have taken quite some time.
Let's jump in to the to this part of it, the cuML library. Can you maybe talk us through the technical underpinnings of this? I mean, is it as simple as, hey, these things love matrix multiplication and we're just doing matrix multiplication using CUDA and it's just faster? Or are there kind of interesting nuances to the way some of these algorithms work that might be worth chatting about?
Well, to start with, a little bit about the architecture of cuML. So cuML is built on top of what we're calling mlprims. These are primitive functions that are composed of even lower level math libraries or various things that have been developed at NVIDIA for certain linear algebra purposes. And so we take these primitives and they are delivered in C++. So then when we need something new, like I have a colleague working on doing massively parallel ARIMA regressions. And so when he began working on that, we already had a Kalman filter primitive and an OLS primitive. And so the amount of new work that he needed to begin composing a prototype was dramatically reduced. Someday in the future, I actually want to see these mlprims wrapped in Python. So different, machine learning researchers or graduate students that aren't experts in parallel programming would be able to mock up the new algorithms they're inventing and be able to leverage the advantages of the GPU.
Yeah, that sounds like a no-brainer. Are the mlprims open source, or are they locked up in a binary or something? I mean, even if they're in a binary, you should still be able to.
Specific thing. Yeah, it's a mix. I mean, so some of the stuff is NVIDIA proprietary stuff, and we've tried to wrap it in a binary, but other ones are more open source. And it's a discussion that we're going to continue to have. But wherever that ends up. Oh, sorry. Go ahead.
Is it a well-documented, set of primitives, or is it kind of internal? Nobody really knows about them outside of the company.
It's something that, I've tried to mention publicly whenever we speak about it. It's not super well documented right now. So you'd need to be able to go into our GitHub folder and look at the primitives folder and be able to read a little bit of C++.
Got it. Okay.
I hopefully want to, wrap these in Python and introduce them to the greater development community to see what else they can do with them. Mm-hmm. Now, you mentioned, are there some algorithms that are more or less tractable to that? I mean, right now, we're working on building a lot of different solvers for more exotic kinds of regressions. And one of the challenges in developing those has been, and this really is where, I'm in awe of some of the thinking of my colleagues. They're essentially sequential algorithms, the way that they're originally designed, right? If you look at the most basic version of like a gradient descent, you start someplace and you keep taking little steps until you're satisfied, and then you stop. Now that's a sequential operation. When we've been doing some early inspections on different solvers, this morning, in fact, a colleague told me that he was disappointed that we were only getting a 3x speed up because he was still trying to think around how to make the algorithm less sequential. So there will be things, just by the way that the underlying math works, that aren't going to necessarily be another 10,000x speed up. But a 2 or 3x speed up, I think, is still pretty great. And the other really heavy intellectual work that is going on right now that we hope to wrap up by the end of the summer or the fall is going to be on multi-node, multi-GPU algorithms.
That's using Dask?
In some cases, it'll use Dask, and we're currently working our way through what other kind of communications layers could be helpful in trying to block up this data and distribute it across a cluster of GPUs in a way that creates a wow moment for the user. Mm-hmm. I know that's a little markety, but that's when I'm looking at what we're doing with cuML. Like, that's what I'd really like. We've been lucky so far that we have gotten some wows with what we deliver, but the underlying algebra and algorithms of breaking some of these things into parallel jobs is very far from trivial.
You mentioned that some of the things that you're doing are allowing you to load your strings onto the GPU. Are you able to utilize the GPU for kind of heavy kind of NLP types of algorithms? I guess for a lot of those, you're kind of numericalizing the textual data anyway, but are there any limitations there one way or the other?
There are some limitations, and we do want to do NLP. We're not quite there yet. We're working on a implementation of Word2Vec. In terms of preparing or understanding your data, we have a lot of ordinary string functions like tokenizers. We have a regular expressions engine, so you can search for regular expressions on strings and substrings and use that to create variables. I think probably closer towards the end of the year would be the soonest I expect us that we're going to deliver that, but it's certainly something that we're interested in and are currently working on. And in terms of like the kind of the pre-processing to NLP is where we started. And so now that we have released and continue to iterate on our string manipulations package, that's going to lay the foundation for NLP practitioners to be able to work in a way that they're used to and have algorithms like Word2Vec or LDA or other things like that open and available to them.
One of the things I'm curious about is in the cuML library, are all of these algorithms and everything you're doing with that library only dependent on the GPU? In other words, are you doing all of the compute in the GPU, or are you using the CPU, as needed or where appropriate? And and I'm wondering more broadly, is it kind of an all or nothing kind of thing, or is the focus really on doing a given operation in the best place for that operation?
I think it's doing a given operation where it's best suited, but we are really just looking at things that are suited to the GPU. All of the
that's actually kind of So doing everything where it's best suited, but everything is best suited in the GPU.
Well, like I said,
Surprise.
for example, our work has been focused on, especially on the cuML side, once the data is in GPU memory, we don't want to move it around. That's kind of one of the big advantages that we have by doing end-to-end data science. We're dramatically cutting down on these read writes. So like the data will come in and it'll sit as a cuDF data frame, and I can immediately pass it into my algorithm and it all stays in one place. So we're able to cut down some of the overhead by thinking really hard about reducing the copies that happen in the course of doing this analysis.
I imagine that there's a bit of a dichotomy or decision point around, do you kind of optimize around these end-to-end workflows, and then everyone who, wants to do anything that utilizes the GPU and takes advantage of what you're doing needs to wait for you to build their algorithm, or, is there some way, if I want to do something that, that cuML offers an optimized version of, but I also need to do stuff that, for which there's not a cuML optimized version, do I need to load, do the 5-minute pen to load into RAM and the load into the GPU and kind of go back and forth each time? Or, is there some kind of scenario where I can load into the GPU and keep the data there, but also do CPU based operations against it? I don't even know if technically that makes any sense, or is feasible.
We have a bunch of different formats you can export data from cuDF. So if you had an algorithm that we haven't built yet, and I'd say anybody is welcome to join in. This is an open source project. We'd love to have any help we can get building these algorithms out. But if you have something that you need to do for work today and you're like, cuDF sounds like a great way to speed up the pandas part of my workflow, but I am going to do a bunch of algorithms. For example, I want to do a bunch of Bayesian stuff. We can export data from the GPU data frame into a pandas data frame, if that's the way we'd like to work with it, into a NumPy array. We support the Arrow data format. And we also just introduced support for DLPack, which plays nicely with a handful of the deep learning packages like PyTorch. So while we're working as hard as we can to add more algorithms to it for the user community, you can pick and choose what's most useful to you at this time. I'd also like to add that cuML can take in NumPy arrays. So these packages were designed to be closely used together, but we know that that's not going to cover all users, and that's not necessarily a requirement.
The other piece of this is cuGraph, and I gather that's a newer, kind of more emerging part of the RAPIDS ecosystem.
Yeah, it is. I don't have the deepest knowledge of cuGraph on the team. I'm not really a graph guy, but I know that their benchmarks have been fabulous, and we're hoping to make more graph algorithms available to people that heavily rely on graph theory in their day-to-day work.
And then maybe switching gears a little bit, beyond the work that's happening in RAPIDS, one of the things that was mentioned at this recent GTC was some announcements and partnerships around creating a reference architecture for data science workstations. What can you tell us about that initiative?
Yeah, the reference architecture for data science workstations is very new, but what I think is exciting about it is that for people that are able to get an NVIDIA data science workstation, we are going to have the software that's going to be heavily based on RAPIDS laid out, ideally so. Once you get the data science workstation, it's loaded with the software that you need to have. That reference architecture will also refer to what we think the best hardware layout is. And And we're just trying to, in another way, make GPU data science more accessible to people. Sometimes, and it's a common project in data science circles to try to build your own deep learning rig. I think that's a great exercise, but it's not for everybody. And I've been in some very, serious corporate environments where IT is not going to let you bring in the computer that you built to start working on their proprietary data.
Right.
And the data science workstation initiative is really about making it as easy as possible for an organization that wants to dive into GPU data science to get started.
Cool. Any parting thoughts from you on RAPIDS or cuML, or advice for folks who haven't really, been exposed to what NVIDIA is doing on the software side that want to explore more?
I would just really encourage everybody to take a look. If you go to rapids.ai, that's a kind of a portal, landing page that will do somebody to everything that I haven't covered here, as well as some of the things that I have, links to documentation, links to GitHub. We've begun a Google group. We encourage everybody that touches Rapids and finds something that they don't like or that doesn't work to file a ticket. You can see our roadmaps and our current work on GitHub, and we really want the community to be involved. Like, as I think about the machine learning algorithms that I'm going to roadmap next for the team to develop on, a lot of that has been informed by customer and community feedback, and it's going to continue to be informed by customer and community feedback. And so I would just, ask anybody that is interested in taking a look, please try to get involved with us, because that's really what's going to measure the success of our project. There's a real open source project, and we've done a great job of building community so far. We've got lots of stars and forks, but we want to see more of those, and we're always happy to see issues opened on GitHub.
Awesome. Well, Paul, thanks for taking the time to share with us what you're up to.
Well, thanks for having me.
All right, everyone, that's our show for today. For more information on any of the shows in our GTC 2019 series, visit twimlai.com/GTC19. Thanks again to Dell for sponsoring this series. Be sure to check them out at dellemc.com/precision. As always, thanks so much for listening, and catch you next time.